Homework 5.1, Systems of Equations, Video 6. Homework due Friday, May 29th at 11:59 p.m. The following video is associated with homework questions 9 and 10. What could go wrong? In the previous 4 videos, we developed 2 techniques for solving a 2x2 system of linear equations. We did substitution, we did addition. And for full disclosure, substitution will always work. Addition will always work. But both of them can go wrong. Now, what do I mean by go wrong? Well, I've got 2 systems set up on the board, and they're almost identical. One of them has a 7, the other one has a 15. But both of them are going to have something go wrong and draw different conclusions at the end. For example, let's say I ask you to solve 2x minus 3y equals 4 and 10x minus 15y equals 7. I would solve this one using addition. For substitution, you would have to solve for one variable, but that will create fractions no matter my choice. So let's attack this one using addition, and let's pick a variable to eliminate. For example, let's say we choose to eliminate the x's. Okay? If I'm going to eliminate the x's, I need to multiply to make these opposites. Now, you can always just reverse the coefficients and change a sign, or you can be a little bit more observant. This is a 2, that's a 10. If this 2 were a negative 5, dang, I just gave away my multiplier. If this 2 were a negative 10, then these would be opposites. So what can I multiply by 2 to get negative 10? Negative 5. Sometimes you can be a little more observant and use smaller multipliers, but in this case, you could have also just reversed the 10 and the 2 and made one of them negative. But let's multiply the top equation by negative 5. Now, unfortunately, I didn't leave a lot of room to the side to pull this off, so we'll just take these results and put them down here. All right, so if I multiply the top equation by negative 5, negative 5 times 2x is negative 10x, I was expecting that. Negative 5 times negative 3y is positive 15y. And on the other side of the equal sign, 4 times negative 5 is negative 20. And the original second equation is positive 10x. I was expecting opposites there. Negative 15y. I wasn't expecting opposites there. Equals 7. Well, I tried to set up the x's to be opposites and unintentionally also set up the y's. Now, I didn't make a mistake. It was destined to happen in this problem. But what are the consequences of accidentally setting up both terms to be opposites? Well, the x's cancel. That was on purpose, but the y's also cancel. That was unintentional, but it happened. Everything on the left is gone. There's nothing left, literally, 0. And on the right side, I have negative 20 plus 7 is negative 13. Well, I got a problem. There's supposed to be one letter left to solve for. There's not. And the remaining sentence is simply not true. 0 is not equal to 13. So what does that mean? Well, here's what happens. If you run out of letters, we've heard this story before, and the remaining statement is false, I ran out of letters, and 0 equals negative 13 is a false statement. Then, we've seen this before, there is no solution. We saw it with inequalities. It is possible for a system to have no solutions. How could that happen? Well, both of these are linear equations. They're currently in general form, sort of. They could both be put in slope-intercept form, but let's not do that because I'll tell you right now, they would have the same slope. Don't believe me? Put them in slope-intercept form. They would have the same slope but different y-intercepts. And equations that have the same slope but different y-intercepts are parallel. So as graphs, those lines would never cross. There's no pair that makes both of them true simultaneously. algebraically, the way no solutions emerges is if you accidentally run out of letters and what you get is a lie. 0 is not equal to negative 13. So, if you run out of letters and the remaining statement is false, you know, I shouldn't say letters, I should say variables. We're more sophisticated than that. If you run out of variables and the remaining statement is false, then there's no solution. So guess what's going to happen over here? Well, the left sides are exactly the same, and if we get rid of the x, or maybe we should get rid of the y, it wouldn't matter. If they're both going to disappear simultaneously, it's going to happen. But if we made the same move over here and said, let's get rid of the x's, and I can do it efficiently by multiplying both sides by -5, then the top equation would transform just like it did before. Negative 10x plus 15y equals negative 20. One moment. This wasn't supposed to be a 15. I'll tell you what it was supposed to be in a second. And left the second equation alone and added the two equations together, everything on the left still disappears and gives 0. But what if we do this and we get something that's true? Freeze. In order to be true, this also has to be 0. So what number had to be here in order to cancel with the negative 20? Positive. I don't know why I put 15 there, but it should have been 20 the whole time. So, sorry. Okay, let's resume. All right, so when we set up the x's to cancel, the y's accidentally cancel also, leaving nothing on the left side, and on the right side, negative 20 and 20 is 0. So now we ran out of variables, and the remaining sentence is true. So, if you run out of variables, comma, and the remaining sentence is true, what does this mean? Well, when this happened in inequalities, it meant that the solution was all real numbers. That's not the case here. We can't say all real numbers because we're not solving for one variable. If we said all numbers work, then that means any pair that we substitute will make them both true. That's simply not the case. If I put in 1,000 here and 0 here, I'm not going to get 4. So I can't say every number works. But what does it mean? Well, here's what it means from a graphical perspective. These lines, they're parallel, but there's more than that. If we put both of these in slope-intercept form, not only would the slopes be the same, but so would the y-intercepts. If you don't believe me, solve each one for y. These are the exact same equation, which means not only are their lines parallel, they're on top of each other. And what that means is every point that's on one line is also on the other. So there are an infinite number of solutions, but they're this infinite number of solutions that lie on the graph of either line. So how do we describe this? Well, we're not just going to say there's an infinite number of solutions, we're actually going to describe them. And the way we're going to describe the infinite number of solutions, and actually in the homework they provide this for you, but I'm going to show you how it's described. If you run out of variables and the remaining sentence is true, then the solution set is written in set builder notation. The set, which we haven't talked about since the very first video when we talked about complex numbers and number systems. So how appropriate that we're in the second to last video, full circle. The solution set is the set of all ordered pairs, so we'll say x comma y, such that, and we have to stipulate what those ordered pairs do. Well, to put it simply, they have to make either one of these true. So we could say 2x minus 3y equals 4. So every ordered pair that makes this equation true is a solution. And there would be an infinite number of such pairs because this graph is a line which contains an infinite number of ordered pairs on it. So to summarize, if you're solving a 2x2 system and you run out of variables, one of two things will happen. What's left will be false or true. If it's false, there's no solution. Easy one. If it's true, then the solution is all ordered pairs that make either equation true. I could have written the second equation here, because frankly, these are the same equations. That should be kind of easy to see. If I divided this equation by 5, it would turn into that one. Would you believe we only have one more video for the whole class?